So good afternoon, everyone. So let's go through the test analysis for today's test, that is 5th of September. So this was the first question. A circular coil of radius r had a self-induction of so and so. If two such identical coils go, what does this mean? If two such identical coils means if other coil also will have same value of self-induction. If this value is L, this also will be L. With a negligible separation, then what is the mutual induction between two coils? Okay, that's what the question is. If you have to visualize, if this is the first coil A and this is second coil B, there are two ways to understand this question. To find mutual induction, suppose current I is flowing in the first loop. So look at, so whatever field is created at a particular point within the loop A, since the loop B also is having same area, is placed very close to first coil, and the corresponding point B also will have same field. So if we take this small equivalent areas here in A and corresponding area in B, areas being equal, field being equal. So when current I is flowing, whatever flux it creates in the area bound by coil A, it creates same flux in the coil B also, which implies the self-induction of A and mutual induction between A and B are equal. Okay, so that's one way to understand. And second way to understand what is the mutual induction, we also understand mutual induction. We write something as A times root of L1 and L2, and it depends on what extent the field lines created by the first coil are passing through the second coil. If all the field lines created by the first coil is passing through the second coil, which many times we say the flux, if the flux is completely linked, K is equal to 1. So if K is equal to 1, 2 being equal, I substitute, it becomes root of L square is equal to L. So mutual induction, both ways you can understand, is same as value of L, and this is the correct option. Next question, which of the statement of conductor is true? I think this is something we can easily check it out. If there's inductor, the potential, there will be potential difference only when the current is varying. So when this question, if when the current is steady, VA will be equal to VB. So this option is out. Let's check in second case, current is from A to B. So that's the direction of current. And so this is what the direction of current is. And if it is decreasing, if current is decreasing, it will act like a battery in the same direction. So this will be the equivalent loop, in this case B. In this case, what is the case here? Which potential is higher? B is higher, which is not correct here. Here VA has to be higher. Similar way, let's draw this one. Current is from B to A. What is direction of current? Let's mark the direction of current, and then we can mark, okay, this is something low, and current is from B to A. Let's mark the direction. This is the direction of current is, and it is decreasing. Decreasing means EF induced also will be in the same direction. In this case, now I find A is at higher potential. In this case, we find VA is greater than VB, which matches with what is required. This statement is correct. Similar way, you can check option D, it will come incorrect. Okay, this looks like a lengthy question. It's collected to wireless on it. Current reaches 63% of its peak value in 1 second. And what does 63% of peak value current mean? How much time does it take to reach the 63% of peak value? So first case, it implies, yes, of course, the time taken is equal to 2. First case, so when it is wound in a particular manner, first case, first solenoid, we will find that tau is equal to 1 millisecond. And what is tau is equal to L by R. What is second case? We need to find now the same piece of wire is rewound. When it is rewound, what will happen is inductance L value will change. And solenoid, because the length is changing and dimension is changing, so what is the time taken to again reach the same 63%? Second case also, what we need to find? We need to find the value of tau only. So now what is the new value of tau dash? That's what we need to find. That will be the time it will take to reach 63% of the peak value. And tau dash, which term is changing here? L is changing to L dash. The distance will remain same because the wire remains same. All we need to do as we change the dimensions of the solenoid, its inductance will change, and accordingly the time constant will change, and accordingly time taken to reach 63% of peak value will change. We have to find how L changes as the dimension of solenoid change. So whenever such questions are there, we can write in terms of parameters which are changing. What is L equal to? Our L is equal to mu naught times n square into volume. Let's try to express in which terms. I try to express in terms of things which are changing of radius of the solenoid and length of the solenoid. These two terms are changing. I'll express the same thing in terms of radius, length of the wire, length of. So what is n equal to? Number of turns. If x is the length of the wire, the particular length of the wire x, and total number of turns will be equal to divide by 2 pi a. That will total number of turns, but we need turns per unit length. We divide by L, thus become the value of n. So square of this is n square term. Volume will be equal to pi a square into L. So other terms are not changing. We are concerned only which two terms we are concerned with A and L. How would it vary with A and L? So if you look at this, A square will get cancelled. X is constant anyway in second case also. L comes proportional to 1 by length of the inductor. So what is L2 by L1 here? First case, second case, what is the length here? Length is L by 2. L by this will be equal to L divided by initial length divided by the final length. This inverse proportion, L by 2 is equal to 2. So what is happening in this case when it is rewound? When the length becomes half, inductance becomes a double. This L dash is equal to 2L. It will become 2L by R. Hence, tau dash will be equal to 2 millisecond. So it means it will take 2 milliseconds to reach that value. That's how this question is. And you look at the calculations involved are not too complicated. These two are fairly direct questions. What is the current that will pass through battery in one time constant? So if you have to calculate the charge passing through, what is delta Q equal to? This is equal to integration of dq. It is paring it by value. So from 0 to tau, that will be equal to I dt 0 to tau. So we can write this is simple integration, and we have done it. I think all of you must have done in the class also, and you also will recall what is current equal to in case of LR circuit. LR circuit battery closest is E by R 1 minus e raised to power t by tau. So it's a simple integration. We can easily find the value. And the second, this question also is really easy one. Okay, so we'll not discuss with these two. These are fairly straightforward questions. Let's look at this question here. So first, let's try and visualize. There are three coils involved here. We'll place coil A at the origin. So we'll draw this coordinate system. This is x-axis. What you have done, and let's this be origin here. This is the coil A, which has a radius of capital R. And the second coil, another coil, small coil B, much smaller radius, is placed with coaxial with A. This is the coil B. Coaxial. This also axis is along x-axis, and radius is much smaller. This radius is R. And third coil is placed at a distance of here x coordinate from here to here. The distance is root 3 R. Okay. So what we need to find here, when coil carries some current, when the current I is this is carrying some current, and this current is varying. So di by dt is has some value. Some value it has. So what we need to do, if it leads to induced EMF in coil B because of mutual induction. This is the coil current is changing in A coil A. So mutual induction in B will be dependent on coefficient of mutual induction between A and B. Similarly, what will happen when you change the current here, the flux will change through coil C as well. There will be induced EMF in C as well. So this question involves mutual induction between A and B, and also mutual induction between A and C. Okay, so let's see what is the mutual induction. So this in this case, see in both the cases, since the coil is small, and we know in case of both coils are placed along axis, the field also will be perpendicular to the plane. So if the field here is B1, since its coil is small, I can consider field to be uniform. And here also I can consider field to be uniform. So what will be the in case of phi1? Current in coil B due to current in A. This will be equal to B into area is equal to B1 into pi r square. Cos theta is 1. And similarly, what is the flux in coil C when the current is in A? B2 into pi r square. And this will be okay. And what does B1 is equal to? In this case, we notice all we need to know what is the field at the center of the coil. In this case, coil length is mu naught I divided by 2r. And this is, here we need to calculate field on the axis of the coil. When the distance is root 3r, what is the field? I think some of you recall the field is proportional to a cube of this inclined distance, and this becomes equal to b by e. So this will be equal to b2. This question is directly based on compared to b1. b2 is 1/8. If b2 is 1/8, flux also is 1/8. Coefficient of mutual induction also is 1/8, and hence the induced EMF also is 1/8. So whatever field is created here, B2 is based on B2 is equal to B1 by 8. Unless some of you may recall, yes, this is on the axis. As you go to distance root 3r, field becomes 1/8. So this becomes 1/8. So EMF also, this will be 1 by 8 of similar term. So mu naught I by 2r. And when you calculate EMF here, di by dt term will be same. Since this is 1/8, EMF also, the EMF will be 1/8. So if it is EMF induced is 1, it will be 1. So answer will be yes 1 by 8, which is the answer. Okay, this ratio of current in branch containing capacitor and inductor. This is fairly simple question. What is the maximum current in the capacitor? The peak current in the capacitor will take place soon after the time t is equal to 0. At time t is equal to 0, what will the current in this branch IC? That's what we need to calculate. And at time t tends to infinity, what is the current IL we need to calculate, which are fairly easy. So we have two circuits when t is equal to 0. At t is equal to 0, this will be open circuit, and this will be like a conductor. So current will flow at t is equal to 0. This is the direction in which the current will flow. This is t is equal to 0 situation. At t is equal to 0, in this case, current IC will be equal to, what is the resistance in this case? 5. Current is equal to 5 by 5, which is equal to 1 ampere. And what will the IL value? How much current will flow at infinite time? At times t tends to infinity, no current will flow through the branch containing capacitor. So at that t tends to infinity, what will be the manner in which the current will flow? The current will flow in this. No current will flow through here. Resistance becomes 4. So in this case, clearly see the two circuits and very easy to identify. Since resistance is 4, this current becomes equal to 5 by 4. And if you take the ratio, we very easily get the ratio. Ratio of P current in the branch containing capacitor, 1 divided by 5 by 4, which becomes 4 by 5. This is something very conceptual question. We know when we break the circuit, when we break the circuit, di by dt is extremely large. And hence, EMF induced is very large. And when EMF induced is large, this leads to high EMF. And if EMF is very high, induced EMF is very high, it will lead to bulb burning very brightly. It will suddenly become much more brighter. That's the condition when the contact is broken. Induced EMF is much higher when the contact is broken. Contact is broken basically means R becomes very, very high. When R becomes high, tau L by R, tau becomes very small. So current can change very quickly. If the current can change very quickly, di by dt is very large, EMF induced is very high. Okay, this is actually past means question, and this inductor, and this is how the circuit is, and P1 is kept for a long time. So initially, what does K1 key kept for a long time implies? It means that we are charging this inductor. Okay, so this it will have a current. What is the steady current which will flow in the inductor? In that, its current will be EMF by resistance and 0.15 into whatever 1000. So that become equal to 1 by 10 ampere. Okay, and that's how it's flowing. Suddenly, then after t is equal to 0, P1 is open. K2 is closed. So suddenly this becomes the circuit at t is equal to 0. It's a discharging circuit. Now what is happening in this circuit? No, battery is not there. So it is about initial current being I naught. It's a discharge circuit. And discharge circuit is a simple equation. We can easily calculate current. In case of discharge circuit, current as a function of time is equal to initial current equal to e raised to power minus t by tau. And we put this values of tau, it comes equal to t comes equal to 5 tau. Hence, this current becomes equal to I naught divided by e to power 5. And e to power 5 substitute 150, you get your answer. And this is how actually the calculation had come a few years back. Okay, circuit's point C is connected to point A. Initially, in this case also, this is the initial state. It is connected. It means circuit becomes constant. It is connected for a long period of time. So when the circuit becomes constant, the current will be equal to E by R. That's the E current I naught flowing. Then suddenly point C is disconnected from point A and connected to B. Again, it's a question of discharge circuit. It's a question of discharge circuit. In case of discharge circuit, what we know, only one thing we need to know, that current as a function of time is equal to initial current e raised to power minus t by tau. That's the case here. So what we need to find, ratio voltage and resistance are equal. So we have to calculate. So what is the, at any two, let's let this two voltages become equal at time t. So at time t, VR is equal to VL. Let's find VR and VL. What is VR? VR equal to, how do you find VR value? I at time t into R. So that will be equal to I naught, which is E by R into R e raised to power minus t by tau. And the time is equal to, the ratio, not equal. We have to find the ratio, we have to find the ratio of voltage VR by VL. And time t is equal to tau. What is this value of t is equal to tau? It becomes equal to by. Similarly, calculate VL. How do you calculate VL? VL is equal to, at time t is equal to L di by dt. Okay. So in this case, if we differentiate, what does it comes to? And L into d by dt of I naught e raised to power minus t by tau. So it becomes equal to L divided by L by tau into I naught and e raised to power minus t by tau is equal to tau here. So this becomes equal to L divided by L by R. I naught is E by R and this becomes 1 by E. When you see those things, both are equal, hence the ratio comes equal to 1. This is a fairly simple question, conceptual question. Maximum is situation A, when the flux is maximum. As the flux keeps reducing, coefficient of mutual induction is reducing. Okay, this question here. So what is being done here? Resistance of the circuit is increasing. So if we keep moving towards right, it's a kind of rheostat situation. More and more resistance will become part of the circuit here. See, what we understand in behavior of inductor. Inductor, if it becomes like a battery only when the current is changing. Otherwise, it will just allow the current to pass through without offering any resistance. So is the current changing in the circuit? Yes, the current is changing. Now, the resistance is increasing. So let's say, first of all, what we understand from here, R is increasing. If R is increasing, the current is not constant. What will happen? That current I is decreasing. Current is flowing and it is decreasing. So this is direction the current is flowing, but current is decreasing. And current is decreasing. If current decreasing, so this also acts as a battery and it will act in the same direction. It will support the current. That will be the value of, that's how EL will act. We don't know its value, but depending on how the current is changing, it will act like this. So in this case, how I is related to voltage and other factors here. Okay. So at this instant, value resistance is 10 ohm. This resistance is given as 10 ohm. What is the value of I? So this is situation given. If you have to find the value of I, we can try find using Kirchhoff loop rule. If you apply Kirchhoff loop rule, what would this be equal to? 5 plus EL which is induced EMF in the inductor, minus I is equal to 0. What is I equal to? 5 plus EL divided by, so 5 plus EL will be equal to 0.5 plus something. It will be a little more than 0.5. That's the answer. This question connected to battery solenoids are placed at large separation but coaxial. So we know in this case, we said if they are at large resistance, we can treat them as one single inductor. There will be no mutual induction. It will be equal to L1 plus L2. Okay. So per time to that is L equivalent. When they are far apart, large separation, that's initial state. What happens when you start bringing them when they're brought close to each other? The moment you class close to each other, the field created, the current in first coil will create field in the second coil and vice versa. So in the final state, what will mutual inductance also will turn up. And in this case, equivalent value is equal to L1 plus L2 plus minus 2M. Why this plus minus? Depending on whether field, how the windings are. If the windings are such that field created are in the same sense, plus sign. If the windings are such that field created are in the opposite sense, minus sign. We don't know whether the windings are same or minus other direction. So what will happen if we don't know this one? This value could be new value of L can be greater than or smaller than initial value. And since L value can become greater or smaller, time constant also may could be greater or smaller. So this direction of winding. Okay, in this case, capacitor C charged to potential V0. So this one is charged to potential V0. So are we saying that this is something in nature connected in the circuit as shown? So initially, what is the energy given to the top loop? Now initial case, this S2 is open. Only S1 is closed. Okay, connected. S1 is closed at time t is equal to 0. This one is closed at time 0. Branch with C. This one is closed at time t is equal to 0. Initial. Okay. After time t, it is open. And what is this time t equivalent to? This time we can easily notice this LC. So the time t is equal to, in terms of time period, is t by 12. Okay. So in this case, and this is open while S2 is closed. So what is happening here? As soon as you open the switch here, current will start changing. And at t by 2, it will have t by 12. There's some energy stored in the capacitor and some energy stored in the inductor. And suddenly, if you open the switch, now what will happen? This lower part of the circuit will have same initial energy as was there at time t in the inductor. Then we establish the lower half energy is contained only in the inductor. How much energy it contains, that's what we need to find. So essentially what we need to find at t is equal to 12, what is the energy in inductor? We easily find the energy stored in the inductor. So initial charge was Q. At t by 12, the charge will drop to root 3 Q by 2. Okay, Q is equal to not easily t by 12 sine 30 degrees. So it will charge Q. And or basically we're saying energy in the capacitor will become 3/4 of the total energy. And energy, this we have, I think all of you easily recall. And energy in the inductor will become 1/4 of the total energy. So at this instance, what is energy stored in the inductor? 1/4 of the total energy. And what are the initial energy? If it was charged to potential V, energy is equal to 1 by 2 CV naught equivalent. This was the initial energy, 1 by 8 CV naught equivalent. So this part of this, once this is separated, capacitor is separated, this part of the circuit will have a total energy is equal to 1 by 2 8 CV square. And as soon as this switch S2 is closed, entire energy initially was here, and later on it will keep shifting. This energy will keep getting transferred between these two of them. So what we need to find, and consider what we need to find the maximum charge on 2C. When would the charge on 2C be maximum? That's what we need to find. For lower circuit, maximum. I need to find Q max. When is charge maximum? When total energy is stored in the capacitor. That's the charge is maximum. What is the total energy? Total energy is 1 by 8 CV naught. And let's see that the charge is Q max, and this is equal to what energy is stored in the capacitor. I will use the formula Q square by C. So this is Q m square. This is maximum charge stored in the capacitor 2C divided by 2 divided by the value of capacitance, which is 2C. That's the maximum charge is stored, and very easily you can find the Qm is equal to, this 4 will get cancelled, 2 will remain here. So when we take a square root, it becomes square root of 2. That's the maximum value of charge. Two capacitors, DC and 2C, are charged to potential difference V0 and V0. So this is C is charged to V0. Charge on this is CV0, and this is 3C charged to 2V. So this charge will be equal to plus 6 CV0. Okay. Initial current in the inductor is 0. What will the charge in capacitor C when the current in the inductor is maximum? So this is question about, so okay, this is LC circuit. So what is the condition for current to be maximum? When would IL be maximum? When energy in the capacitor is minimum. This is maximum when energy stored in the capacitor is minimum. When is the energy stored in capacitor is minimum? Okay, so basically this is di, so we can understand here if the current is I here, di by d, if this is maximum, di by dt is equal to 0. Potential difference across these 2 points have to be 0, which you have seen. One way of solving this would be potential difference across first capacitor and second capacitor will be equal and opposite. So, and this question is based on here, energy in the capacitor will not become 0. There are 2 capacitors connected, and these 2 plates form an isolated system. Initial charge on this was, net charge on these 2 put together is minus CV0 plus 6 CV0. So net charge on capacitor, net charge on these 2 plates here will remain same. Initial charge will equal to minus CV0 plus 6 CV0, which was equal to 5 CV0. It will remain, this charge between these 2 of them remain 5 CV0. So any stage, the question is how should I distribute the charge 5 CV0 in the 2 plates so that potentials become equal and opposite. So potential becomes equal and opposite. See, if both signs should be same, if this is plus, this also should be plus. So what will happen from here to here, increase in potential, from here to here decrease. So I have to decrease 5 CV0 so that potentials are equal, and potential is Q by C. So if your potential has to be equal, charge distribution has to be in proportion to the capacity. So I have to distribute charge 5 CV0 in which proportion? In proportion of capacitance. In proportion of 1:3. Or this one should receive 1/4 of the total charge, and this should receive 3/4 of the total charge. So what is the charge distribution 1/4 of this? So C will receive, this side is C and this side is 3C. This will receive a charge equal to 1/4 of this. This will be equal to 5 CV0 by 4, and this will equal 3 into 5 CV0 by 4. So we need to find charge per charge on the capacitor. That's the answer. What is the other way we could have found? This other way, if you recall, if energy has to be minimum, I assume the charge on, if these 2 capacitors are connected. Another way of solving this question is, let the charge on this capacitor is Q. This becomes minus Q. And since the total charge on these 2 plates put together has to be equal to plus 5 CV0, so this charge on this becomes equal to 5 CV0 plus Q. What we'll do here, again, second way of finding, we'll calculate the energy stored in the capacitor. And what has the value of Q so that it becomes minimum? Then we'll write the energy stored will come in form of Q. It will become equal to Q square by 2 into C plus square of the charge 5 CV0 plus Q whole square by 2 into capacitance, which is equal to 3C. And then DUC by DQ has to be 0. Value of charge should be such if it has to become maximum, minimum, its derivative with reference to Q has to be 0. We can solve this fashion also, we can get the value of Q. This is charge Q naught and is connected to a switch and inductor as shown in the figure. Switch is closed at time t is equal to 0. What is the current in the inductor when the charge on the capacitor drops to Q naught by T? This is also a very simple question based on conservation of energy. When the charge, so the total energy initially, so this is total energy, it will get distributed in two forms, UC and UL. Initially at T is equal to 0. What is the total energy? Q naught square by 2C. And that thing is in capacitor. This is 0. What will happen? What we have to find current here when this drops to Q naught by 2. So here, what is the energy stored here? Q naught by 2 square by 2C. Plus, what is the energy here? By to find 1 by 2 Li square. That has to be equal to Q naught square by 2C. Or other way of thinking is this is the total energy. Now this has become 1/4. This energy is 3/4 of the total. So we can equate this term equal to 3/4 of this total. Anyway, we can solve. Find the time. So okay, C is given, L is given. So we can find the value of basically per time period. Find the time after energy stored in electrical field is 3 times the energy stored in the magnetic field. Okay, so if energy stored in the capacitor is 3 times, what has to be the charge? Which is pretty simple. Q has to be equal to √3 Q naught by 2. That's the time when the energy stored is. And when would this happen? This would happen when phase. Okay, so energy stored is. How much time does it take? So if you look at the phasor, initially entire thing is in capacitor. In terms of phasor, if you look at the initial state, charge phasor is like this. This is Q naught. So question is, this is something, how much time it will take for energy stored in electric field is 3 times energy stored in magnetic field. So it has to become equal to √3 Q naught by 2. And for this, what is the angle here? So phase has to change from 90 by 30 degree from here. How much time does it take for phase to change by 30 degree? That's what it's asking. The charge has to change from Q naught to √3 Q naught by 2. Meet this condition, question how much time it will take for 30 degree, the time taken will be equal to time period divided by 12. 30 degrees, 1/12 of the full 360 degree. And what is time period here? Time period is 2 pi root LC. You can easily get your answer. And you can easily solve. Okay, this is based on graph, velocity, and we have to find displacement. Okay, all we need to understand, any instance slope of displacement time graph is equal to velocity at that instance. When used at any instance, basically slope. With this, if you draw a tangent on any time on displacement time graph, and the slope of the tangent has to be equal to instantaneous velocity. So let's look at this from here. So what you have done here, from here to here, velocity is constant. The slope also has to be constant. So up to a square passes, the slope is constant. What has to happen between point 1 and 2? 1 and 2, the slope is positive but decreasing. So this part, how should I interpret the slope? Slope is positive. Slope of xt curve, slope has to be positive, but slope has to be decreasing. And finally, it decreasing to, slope should become 0 at point 2. So if I look at this from here, the slope has become negative. That's why this is not correct. Okay. In this case, velocity positive, the whole thing is gone downwards, which is also not correct. The displacement is positive. When we come to this shape here, that seems all right. The slope is constant here up to this point. From here, slope positive drops to 0. This seems to be the correct option. And you continue, you check all these things here. From here to here, the slope becomes negative and slope keeps increasing. And again from here, again the slope becomes 0 at this point. At some point 9, the slope has to become 0. So this is a graph which matches with that, all these conditions. Okay, circuit shown energy stored in capacitor and inductor are equal in steady state. So it is a steady state condition. In steady state, what we need to calculate, what is the energy stored in the capacitor, what is energy stored in inductor. So in here, the current will flow only in this branch, and this part will have potential difference. So we need to calculate energy stored in the capacitor. We need to calculate the potential difference. So what is the potential difference between 2 points capacitor is connected to? Current is flowing in this loop, this part of the circuit only. So here it is connected across resistance R. So current is equal to E by 2R. So potential drop across these 2 points into R. The potential drop is E by 2. So it's equivalent to saying this capacitor is connected across potential of E by 2. So what is the energy stored? 1 by 2 CV square. 1 by 2 C into E by 2 square. So energy is stored in the capacitor. And what is the energy stored in the inductor? 1 by 2 Li square. And what is the current which is flowing here? Current is equal to E by 2R. So that will be equal to 1 by 2L E by 2R square. So if 2 are equal, just we opt in this condition. Okay, so let's look at this figure, and I say some of you might find it tough, but let's look at this fairly simple question. What is given in the graph? Actually, this graph gives you relation equation between V and X. This gives you equation between Vx. This y coordinate is V and X. And can we write this equation? It is of the form y is equal to minus mx plus v. So slope is negative. So what is value of y? V. And what is the slope equal to? Minus of v naught by x naught. X and c values plus v naught. That's what is given here. And what we need to find, I have to find a x relationship. So basically, I have to find first equation between a and x. To find graph, first I need to find equation. Find equation for a acceleration. And this is what is known. How do I find equation for acceleration? Since it is v and x are given, I will take dv by dx. First, I'll find dv by dx. I'll find a using v into dv by dx. First, I'll find dv by dx and multiply by v. So what is dv by dx? Fairly easy to find here. What is dv by dx? It comes equal to minus v naught by x naught. Thus, what is acceleration equal to? The value of v into dv by dx is equal to minus v naught by x naught and minus v naught by x naught x plus v naught. So what we find here, the slope becomes positive. So it becomes equal to v naught square by x naught square into x and minus v naught square by x naught. What is this nature of the slope? This is of nature, slope is positive, y-intercept is negative. So this slope is positive, y-intercept is negative. That's the equation between a and x. Okay, capacitor, this is a charge to potential V. This is also LC circuit. Let's try and visualize what is given here. So this is capacitor connected, and this is. So I need to find here, potential drop across capacitor. Initially it was 12 volts, it has dropped to 6 volts. It means I can say the charge has become equal to Q naught by 2. Initial charge by, so charge has become half, or energy is stored in the capacitor. If charge has become half, it has become 1/4 of total energy. So what does it imply? If this energy has become 1/4, charge drops to half, energy becomes 1/4. Energy stored in the inductor is 3/4 of the total energy. Now let's write the equation at the instance when the current is I. So basically the equation is 1 by 2 Li square is 3/4 of the total energy. And what is the total energy stored in the, because initial energy is equal to total energy stored. And I'll write, since the potential is difference is given, I'll write in terms of 1/2 CV square. Can we easily solve this equation? And if we put those values, what are those values are equal to? We can easy to solve, and you can easily find value of current. All right, this question is speed of the particle will be maximum after how many seconds? So this is VT graph is given. Since we are interested in the speed, why not we draw VT graph? In this case, very simply, we need to draw a VT graph. And once we draw VT graph, we can find out where speed is maximum. It doesn't matter the sign. So wherever y coordinate is maximum, which is speed y coordinate is been V, that we can find. So what is given starts from rest. So this is initial is 0. And here acceleration is negative and constant. Slope also will be negative and constant. So let's draw the VT graph. What would VT graph look like? So from here up to 4 seconds, slope is 10. So minus 10, slope is equal to minus 10. So here the value become equal to minus 40. What is this value here? Minus 40. Speed is 40. Thereafter what happens? Slope becomes positive. From here, so slope up to 10. So from here, if we mark, this is 8, this is 10. And slope is same value, but opposite given sign. So if I draw this curve here, it will be like this. That's a motion. So when does the speed becomes maximum? Yes, the speed is the maximum value of, that's a point where the speed becomes maximum, which is at 4 seconds. Okay, this is a, I think, is a fairly simple question on mutual inductance. Primary and secondary coil. There's one primary coil A and this coil B. There's a mutual induction. Resistance of primary secondary coils are 20 ohms and 5 ohms. To generate a current of, what is the current we want to generate here? We want to generate a current of 0.4 ampere. What is, we need to find what is dA by dt. Okay, to generate this current, what is the EMF needed in the second coil? EMF needed in second coil is IR is equal to 2 volts. So this has to be equal to, what is the rate of change of current to generate a current? So this has to be equal to, EMF is equal to M dIA by dt. That's the equation. We have to generate a EMF of 2. So we substitute 2 is equal to EMF is 1/2 and dIA by dt. So rate of change of current in the primary coil is equal to 4. So what will the rate of dissipation of heat in the resistor at the instance when the rate of transfer energy to inductor is maximum? This is a typical circuit of charging and inductor. Ideal inductor and a resistance. Ideal inductor means resistor, this itself doesn't have any resistance, only resistance is the external resistance. And it is connected to battery. We know when is the power transfer to inductor is maximum? When current is equal to I naught by 2. That's the time when the power transfer to inductor is maximum. So when it is I naught by 2, can we calculate what is the rate of dissipation of heat in the resistor at this stage? So rate of power dissipated, rate of heat dissipation, power dissipated in R at that instance. Power dissipated depends on the current. At the instance when the rate of transfer, rate at which energy is being stored in the inductor is maximum, current is maximum by I naught by 2. So power dissipated will be equal to I naught by 2 into R. What is I naught here? What is a maximum current, which will be equal to 5. So 5 by 2 square into resistances. Okay, this is a circuit, certain instance current is 5 amperes and decreasing at the rate of 10 to the power 3 ampere per second. So this also, to find potential difference between 2 points, what we need to do, this also we can replace with the battery. And EMF which direction the current is decreasing, so it means EMF will be in the direction of current. And what would be the EMF in inductor? It will be L di by dt. L is equal to 5 into 10 to power minus 3. And this is equal to 10 to power 3, is equal to 5 volts. I put this as a 5 volts and then write equation. VA minus 5 into 1 plus 15 plus 5 is equal to VB. We get VB minus VA. Easy. That's all. I think this we covered all the questions, and I hope most of you should have well. Okay, thanks. I'll stop here. Thank you, everyone.